Okay, this is the outline of my presentation. Firstly, I will present the main principle of shock produced by laser plasma. And after that, I want to present applications for two kind of materials. The objective is to show you that we can do many things with shock produced by laser for dismantling on stripping. First, I will discuss about coatings for painting. This is a stripping painting. And after that, show you for new developments concerning the dismantling of laminate, and in the case of the framework on another project, European project called Recreate. This is some principle of the techniques. First, we use our lasers, high energy lasers in the range of few joules. You focus the lasers on the surfaces, and we create, a plasma. Plasma is a high pressure gas with electrons and ions. The pressure is the range of few gigapascal. And so in reaction of this plasma release, we generate a shock wave, a strong shock wave inside the material in the same range of pressures, of stresses in the range of gigapascal. And I forget that laser pulse duration is a range of nanoseconds. So inside the materials, we have shock with duration in the range of nanoseconds on high pressure in the range of few gigapascal. For the scope for industrial implementations, we use specific techniques with confinement materials. This is transparent materials to the lasers. And we confine the plasma between the two materials, the confinement materials on the material target. And the advantages is for this configuration, we have very high pressure compared with no confinements, and higher pressure at the same power density. It's very useful for application because we need very low laser energy, low in the range of joules compared to few tens of joules. And for materials, we use waters, and it's very applied to and renew, and it's very cheap. It's very easy to use these techniques for industrial applications. So what happened? What are the applications? We have two kinds of applications. The well-known application concerns the use of shockwave produced by laser for to increase the mechanical properties of the materials. Is the laser shot pinning. But for today, I discuss about the use of shockwave propagations, dynamic processes of shockwave propagation in these materials to solicitate mechanically materials inside. So for the laser shock application development, there are many issues concerning the laser interaction to control well the loadings induced by lasers on the materials. We have some issue concerning the materials behaviors under shocks. We have some damaging because, for example, dismantling, the objective is induce damage at the good interfaces to separate materials. So we discuss about few words about impact of interface adhesion properties and the processing. And we are related to, for implementations and for many kind of type of configuration, we have in relation with laser technology. And we need, in fact, to check that we have some good dismantling or good effect in the materials when in relation with NDT techniques. And at the end, we will see in the next talk by University of Patras, we are very related to modeling development because we have many parameters concerning lasers, concerning laser configuration beams, concerning materials. We need modeling to help us to design the processing. So this is a space-time diagram showing the stresses inside the materials as functions of space inside in depth and time. In straight right, we can see that we have the shockwave propagation inside the materials is reflected at the rear free surface as a release due to the conservative laws at the interfaces. and this stress release meets the incident one. At this point, we have a very strong tensiles, and it's high enough we can break the materials. This is a spalliations phenomena, and if we are on interfaces, we can break these interfaces. This is a principle of the techniques for with one pulses. So we have very local stripping. We have no impact, and no, it is not intrusive of materials properties. It works for all materials and is very sensitive to interface properties. To have an idea of parameters, for example, for 10 nanosecond pulse durations, we can remove 60 micrometers for metals, and is a range of 3 tenths of micrometers for polymers and composite. So this is a very well-controlled laser pressure loadings, but for a quantitative approach, we need, by simulation, we need know the equation of states of materials under high strain rate and pressures, but we need to have free surfaces to generate the spalliations. And in fact, we have limited by laser technology, because we have, for one laser, we have 1 pulses durations. In the futures, we want to develop new lasers to have pulse shapes from few 10 nanoseconds to 100 nanoseconds to, in fact, move these loadings and go deep inside the materials and control the depth of these tensils for spalliations. This is a recent examples done on paintings. I show you first the stack of materials. The first one is a representative of painting. This is epoxy resins, paint of aluminum materials. This is for aeronautical applications. Now, the thickness of the epoxy is in the range of 40 micrometers. And the objective of this work is to see the influence of the thermal aging conditions on the adhesions of the interfaces. And so the parameters we can use for strippings. And is representative of end of life of materials. This is accelerated thermal aging conditions with different durations of aging at the temperatures of 120 degrees, and for several thickness of materials. So this is an example of test on strippings with 2 materials. The first one is an age material, is a initial state of the materials, and the second one is for age materials with 68 hours of agings. But we can see first that we can remove completely the paintings. We have a complete stripping of the coatings, but the levels of this threshold stripping is different from the 2 materials, and shows that is very sensitive to the state of the materials. This is we gather all results for the different age materials from initial state to very high thermal agings, around 500 hours of agings. Alors, we can see the line between the blue and the red zone correspond to the thresholds, debonding thresholds, the stripping thresholds. We can see first that it increased for the first step of aging at 24 hours, and it decreased after that. So it's very strange, because we attend that there are some degradation during the agings, but when we try to see the chemical state of the materials, and we measure the TJ temperatures for each state of the materials, and we can see, in fact, that it increased for the first step and is decreased after that. So, in fact, due to aging, we increase the properties of the materials, and after we have degradations of the materials. In fact, we demonstrate that we have a fails in curing processing and to reach and we reach the best adhesions only with agents. So it shows that the techniques success to detect the aging degradations and show fail in manufacturing, but it shows also that is very sensitive of the interface properties and the chemical properties of the materials So it works at the two tables, the two graphs is for different thickness of the materials, and we have the same behaviors. Alors, this is a view of the macroscopic observations of the stripping zone, the stripped zone for the two thermal aging durations. First, on the left, this is initial state of the materials, and on the right is the age with 168 hours of aging. We can see that we have the state is very different because we have a change of interfaces properties from adhesive bonding on the left and cohesive adhesions of the on the right. It shows that in fact we break the materials not at the interface because the interface is very good, but near the interface, but in the volume of the materials. So it demonstrates that we need, for example, for the stripping of the coatings, we need to adapt the laser parameters as functions of the age of the coatings. Alors, I show you an example for one materials interfaces for coatings, but in the life we need to dismantling materials like laminate with many interfaces because we have ply, interply, we have adhesive bonding with different thickness. But the question is, can we adapt the laser beam, the laser loadings to have selections of the separations for each interfaces. Alors, to do that, we have developed different techniques. Alors, first, if we remember the first configuration of the space-time diagram with one pulses, but we can generate unset tensils near the refer surface, and we can reach interfaces in the depths of the materials. So we have developed two other techniques with two beams. The first one with impact on the two fronts of the materials, and we play between the delay between the two pulses. And when we play with the delay between the two pulses, we can locate the tensils inside the materials where you want. And it's very interesting to go in depth of the materials. And another techniques, actually very useful for us with the two beams, but we solicitate and we impact with the lasers the two surfaces of the materials, and we play between the delay between the two laser pulses, and we can adapt the delay to have a maximum tensile inside the materials where you want, and especially at the interface we want to solicitate and we want to damage for separations. This is a view of the processing. This is a framework on another project, REN projects, is to show you the process environments and in your lab. Well, this is for the adhesion test, but it's not for dismantling. It's to show only the configuration. It's not easy to proceed because we need to have two laser beams, and we need to move the parts, the structures on the lasers. We can see we have the two laser beam. We need to have the confinements, and we shot with the lasers on the two sides of the materials. So it's not easy to implement, and it needs a very important engineering developments to introduce laser, to introduce parts on the laser beams. Alors, this is a well-known examples. I think it for us the first example, the first publications on this processing has been done in 2017. We try to do the demonstration that we can damage the materials inside the materials where we want. On the left, this is the pictures. In green, we can see the delaminations. This is for the configurations in the middles of the samples. And when we play with the pulse durations, we can see that we can move the damage inside the material. So we had a very well controlled of the damage inside the materials in playing only with a delay between the two pulses. Alors, we have done an extensions with not only one damage, but in the framework on Laurent Berthe PhD, we have done a large part. This is 10 centimeters by 10 centimeters laminate, and in fact we create 72 damages inside the material. This is a C-scan ultrasound techniques to detect this damage at the middle of the materials, and we play with a delay to introduce damage to represent engine inside the materials. So this is time of flight cartography, and we can see that we have damage at the different depths inside the materials. This is the external state of the materials. We can see nothing showing that we have no damage inside the materials. Alors, what is the futures? Actually, we have in the framework of new European project, Recreate, working on the recycling of composite. We extend this this process for the first composite laminate disassembling. First for one ply on the left, we use the first configurations with one pulses, and on the right, this for to separate laminate where you want inside the materials, and we play with symmetrical configuration. Alors, in this case, we separate in the middle the materials. It's worked very well. We can see some example. One example on the left, we want to separate on the left. Alors, this is in the middle. The thickness, total thickness is 2 millimeters. Alors, the size is in the range of a few tenths of millimeters, but actually we work on larger plates in the range of few tenths of centimeters. So, we can see the separations of the materials in the middles with the respective thickness of 1 millimeter for each part. And ply disassembly, we can separate ply by ply the materials. And I show you only for one ply separations, but we have demonstrated that we can separate one ply after another one, another one, another one. And we can, at the end, for this case, we have, I think, 5 of 6 ply. We have, at the end, 6 plate of one ply for the reuse the materials. And it's very interesting because we compare mechanical properties before and after separation, and we have the same mechanical properties and same physical integrity of the materials. Sometimes we have some cracks, but in this configuration, in fact, we use the maximum pressure we can reach with our lasers. The objective is to demonstrate that the highest loadings, we have no damage inside the materials. So we have no damage in the materials, and we compare mechanical properties. And in the table, we can see that we have the same mechanical properties for the part we compare if we compare the reference samples and dismantling samples. Now the next step is now to reassemble the materials and check if we have the same properties for the reuse of the materials. So we reach, in fact, with this project, a kind of the loop between the end-of-life materials to the new parts to be built by this dismantling materials. And we can go on the website recreatecomposite.eu to see some results and this framework of reopen project. So for the last parts of my talk is very short. Demonstrate that the process work very well in your labs, because there are no contrast, industrial contrast. And what is this industrial contrast? First, we need to have lasers in the range of a few joules. That is not easy to move or to implement. We can, for example, it's difficult to use fibers, optical fibers for beam transportation, but we need to have do an engineering works to implement this kind of lasers. We need to have a very good laser stability, because during my presentation, I showed you that it's very sensitive to many parameters on interfaces, materials, on many parameters, that we have a very good stability and reliability of the laser, but it's done actually. We have the laser with very good parameters. Alors, it's not, it's for experts in the lasers. We need to have a very good laser beam quality. Donc actually, we use diffractive optical elements to ensure that we have top hat lasers, spatial top hat on the surfaces. And it's another fact, we need to protect coating the surfaces from plasma thermal effect and uses additional coatings. Now, another contrast, if you want to dismantling large parts like in aeronautics, the part that's several meters long, we have sort of curvatures, there are thickness variations, so there are many, but we demonstrate that in playing with all laser parameters, we can adapt, and it's very versatile techniques, but we need to have the technology to do that. And there are some general environmental conditions at the end, because we can use these techniques for maintenance, for productions, and we can perhaps move to worldwide, for example, for maintenance with different temperatures, humidity properties. And so we need it's another aspect for me. We need to have no waters confinements. We have developed during next years new materials. It's a composite, it's a polymers materials for the confinements. So this is the point for engineering applications. We have done many progress in all things, and I think is ready for to think about implementations of the technique for industrial applications. We can see in these papers and examples, not for laser dismantling, but for lasers shot pinning, but it shows the last developments for process development and future implementations. Now, what is the futures? We need to progress on the design of the process, because we see that we have many configurations, and we need to play with all these parameters and configurations to adapt the process for the applications. And so at the end, we need to try to implement more precise parameters concerning the interfaces and adhesion forces as functions of properties, and in relation, in fact, with end of life of materials. So we need to have the futures numerical code for the design process, and in fact for the process control at the end, to ensure that we have no damage and no impact inside the materials, dismantling materials, to analyze online or at the end of the process if we can use the materials for new applications. And I think it's a pleasure to me to introduce, in fact, the next talk from University of Patras, because I think the work they did inside the framework of Morpho is the best advancements, demonstrations for this first step of these future challenges.